Hello, my name is Hilary Weller and I'm at the University of Reading. This talk is about long time steps for advection. This is done by extending MPDATA to use implicit time stepping. The talk is with James Woodfield, who's doing a PhD with me, Christian Kuhnlein at ECMWF, and Piotr Smolakiewicz. The motivation is that atmospheric models can have severe time step restrictions due to advection. This can be due to, for example, the poles of the latitude grid, large updrafts in combination with small delta Z, small grid spacing in the vertical, just unusually strong winds. This is usually solved by using semi-Lagrangian advection, but this is at the expense of conservation. Semi-Lagrangian is not conservative. So I would like to answer the question, can advective time step restrictions be removed by using implicit time stepping? This is the list of requirements that I'm working with in order to develop an implicit time stepping scheme for advection. These requirements are motivated by the knowledge that the current number is only high in small regions. I want accuracy and cost comparable with explicit time stepping, where the current number is less than 1. I want the scheme to be stable and at least first order accurate for a current number greater than 1. I want it to be monotonic, or optionally have an option to be monotonic for all current numbers. I want it to work on arbitrary meshes. I want exact local conservation. I want it to be multi-tracer efficient. I want good parallel scaling. And I'm also asking if implicit time stepping can be used just locally rather than over the whole sphere. One of the problems to overcome is the order barrier of Gottlieb et al. 2001, which states that no implicit method exists with order greater than 1, which is monotonic for all time steps. The proposed solution is to revert to first order accuracy locally where the current number is high. This poses a question about having a scheme that changes locally, whether it's either implicit just locally or changing in order of accuracy locally. Consider this time stepping scheme. For conservation, theta, the off-centering, must be inside the divergence. So I've changed equation 1 to equation 2 with theta inside the divergence. But now the advecting velocities have become 1 minus theta u and theta u. The velocity field started out divergence free, but these, now I've multiplied the velocity by 1 minus theta and theta, these are divergent. Does this generate spurious oscillations? In fact, if the spatial discretization is first order accurate, it's straightforward to prove that equation 2 with theta inside the divergence is monotonic as long as the off-centering is greater than 1 minus 1 over c. This is as expected. If the current number is less than 1, then theta it can be less than a half, so it can be an explicit scheme. If the current number is greater than 2, you need theta greater than a half. If the current number was equal to 2, then Crank-Nicholson theta is a half would be monotonic. If it's greater than that, current number is greater than 2, you need theta to be smaller. I'm now going to describe how the infinite gauge version of MPDATA is extended to use implicit-explicit time stepping with off-centering theta between 0 and 1. First, you need to set theta to be 1 minus 1 over current number. I'm using actually 1 minus 1 over the current number plus a quarter for a safety margin. However, for small current numbers, that can give a theta less than 0, so it's set to be the maximum of that and 0. As is usual with MPDATA, you start with your diffusive first order update, but this one is now mixed implicit explicit, but first order upwind spatial discretization. Then comes the explicit correction, and this is still an explicit correction. So the second order update is the first order update plus this correction. This is the same as the standard MPDATA correction if chi is equal to 1. And for when chi is equal to 1, when theta equals 0, which is when the current number is small. However, if theta is greater than 0, if there's any implicitness, then the correction is adjusted slightly to maintain second order accuracy. However, this becomes unstable if chi is less than 0. So once the current number gets big enough and theta gets big enough, this has to be limited. Chi has to be always kept greater than 0 for stability. So then you lose second order accuracy when the current number is greater than 2. In this correction, the divergence is calculated using Gauss's divergence theorem, standard finite volume, and the gradients inside here are calculated using centered differences. N hat is the normal to each cell face, and delta x is the cell center to cell center distance. Flux corrected transport can be applied for monotonicity. This uses the Zalesak 1979 limiter, but with a crucial difference. The old time step solution cannot be used to provide local bounds on the solution because, with large current numbers, the old time step solution is not local. The extrema can be more than one grid point away from the next time step. So only the diffusive solution can be used to provide local bounds. I'll show solutions on a variety of meshes of the sphere. Here we have a full latitude-longitude grid, but with a polar cell, and a skipped latitude-longitude grid where resolution is reduced towards the pole, a cubed sphere, and a hexagonal icosahedron. These are the results of the DCMIP test case of deformational flow on the sphere. These results use the full latitude-longitude grid but rotated 30 degrees so that there's flow over the pole. The two poles are here and the contours show where the current number is greater than 1. With the flow over the poles, the current number gets up to 70 for this test case, and you can see that the tracer is advected through the poles where the current number is large without any obvious problems. These are the results on the skipped rotated latitude-longitude grid. So now the current number is much reduced. The current number always stays less than 2 for this test case. And on the cubed sphere grid, you can see here the current number is slightly larger at the corner of the cubed sphere, and over the course of the simulation the current number remains less than 3. And on the hexagonal mesh, the time step is chosen so the current number is less than 2. Using implicit time stepping, it's important that the number of solver iterations does not scale with the current number. The number of solver iterations should increase slower than the current number. Otherwise, there's no point in using it. You might as well just take fewer time steps. This graph shows the number of solver iterations per time step on the unrotated lat-long meshes. The different colors show different current numbers. So that current number of 1 or less than 1 is in black, current number less than 2 is in blue, and current number less than 10 is in red. So you can see that as the current number increases, there's a lot more iterations are taken. However, I realized that the solver tolerance was way too tight, 10 to the minus 12. When I reduced the solver tolerance to 10 to the minus 6, which is this green line, the far fewer iterations are taken and with no impact on the solution. Of all the black lines, all the blue lines and all the red lines, they are the different black lines, blue line and red lines show different resolutions. So you can see that the number of iterations is not dependent on the resolution. To conclude, I will review the list of requirements that I put up at the beginning. Can we get accuracy and cost comparable with explicit time stepping where the current number is less than 1? Well, yes, because with this scheme, when the current number is less than 1, it is an explicit scheme. Is it stable and at least first order accurate for current number greater than 1? I haven't shown all of my results, but yes, and there's also some numerical analysis that shows that it's stable for current number greater than 1. Is it monotone for all current numbers? Yes, the flux-corrected transport can be adapted for implicit time stepping. It works on arbitrary meshes. We have exact local conservation. It can be made multi-tracer efficient by using the same preconditioner for all the advected quantities. The preconditioner depends on the advecting velocity, not on the quantity being advected. I haven't looked at the parallel scaling. The implicit time stepping can be used locally. In addition, we've seen that with implicit time stepping, we can increase the resolution without having to reduce the time step, and this still leads to improved accuracy. We've also seen that the scheme is second order accurate as long as the current number is less than 2, and first order accurate for a current number greater